Good evening, Earth Science students. Today's lesson to classify the various types of stars. Now, this lesson it kind of covers two lessons in one to combine stars. Once again, the Earth Science curriculum is very vast. It's a lot of information, so these lessons are made so we can condense them into one, and we'll have a lot more questions to work on in class, and the ability to use the reference table. All right, so to get you guided notes, the ones I gave to you from class, and put in the proper terms. At the end of this, you'll be able to update your vocab based on some definitions. All right, let's begin. Stars. A large ball of gas held together by gravity that produces tremendous amounts of energy and shines. All right, and there's a many-step process, about 5 or 6 step process to make a star, which I'll go over with you. The sun is the dominant gravitational force associated with all of these celestial bodies in the solar system. All right, the word celestial means outside of the atmosphere, at least the Earth's atmosphere. All right, and so we have planets, we have asteroids, we have comets, we have our sun and other stars out there. Stars are classified based on their 1. Size, 2. Temperature, 3. Color, 4. Luminosity, its brightness, 5. Its age. And this is all found on page 15 of your ESRT. All right, so on page 15, we have different ages. We have the earliest stage, the main sequence. We have an intermediate stage for our giants and supergiants. We have our late stage stars, which are white dwarfs. All right, and there's a few stars that are there for you. So on the regions, they can ask you information about any of these stars or make comparisons, make contrasts between these stars. All right, so regions question. A white dwarf star has a temperature of 13,000 degrees Celsius. What is the probable luminosity of the star? So let me go back. Surface temperatures in Kelvin. All right, we have to make a small conversion, and this is how you would do it. We'll learn more about this for weather, but right now you kind of should know how to do this. All right, so conversion. So nice and easy. So I find 0 degrees Celsius, and if you go across from 0 degrees Celsius, it's roughly about 273 Kelvin. So what you do is, anytime you have a Celsius reading, you would just add 273 to it. So in the question, 13,000 degrees Celsius would be really 13,273 Kelvin. You're just adding 273 to it. All right, so if you go back to the question, right, I'm going to put a line here where I think the 13,273 line would be, approximately. And we had our 4 choices. We had a luminosity of 100, 10, 0.1, and 0.01. And it was referencing a white dwarf. So 100's good for the main sequence. 10 is probably good for the lower portion of the main sequence. 0.1 kind of touches a few stars for the white dwarfs, but if you notice the 0.01, it's really close to the white dwarf late stage section. All right, so based on this question, we'll come up with 0.01. That's the brightness of a star for a white dwarf at that temperature. All right, stellar evolution. All right, we have the birth of the star right at the very beginning. We have what we call here a nebula. Gas and dust clouds together. Eventually, they would be under gravitational contraction. Right, it comes together. So star formation, gases and dust would condense. Look at all the arrows going in. Next, we have the main sequence where it matures and ages. So our sun is maturing, like as mentioned in class. Eventually, our star will die. And since our star is a medium-sized star, it's going to go down this avenue here, down this highway. A bigger star will go the other direction. All right, so we have the recycling of stars. So if it's a large star, eventually it's going to blow up, what we call a supernova, and all that matter that it created goes out into space and it can get recycled. And the remnants, what's left over from a very high mass star, can be a black hole or it can be a neutron star. Right, so those are your remnants. Down here for the low mass, like our sun, can eventually kind of grow into a red giant, and then from the red giant loses all of its power and it's left with the core, which is the white dwarf. And eventually, once all the energy is used up, it's going to become dimmer and dimmer and dimmer into your black dwarf, right? Which is the death of a star. All right, stellar evolution. We have 6 steps. First one, all stars begin as a swirling clouds of gas and dust called a nebula. All right, so in the sky, sometimes you can see pictures of this in class, or if you ever go to the planetarium in New York City, sometimes you can see these swirling clouds. They're pink in color, a little bit of red, sometimes blue or green. They're beautiful pictures. All right, those are your nebulas. Those are like the preliminary star formations. Number 2, collection of gas and dust particles in space grow prior to what we call nuclear fusion. And this is called the protostar. All right, this is before the formation. All right, number 3, as the nebula is compressed by gravitational forces, remember the arrows going in, the core of the star becomes hot and nuclear fusion begins as temperature and pressure increases. So all the matter begins to fuse together, and that creates energy, right? Heat's involved, and a whole bunch of wavelengths are also involved too. All right, and 4, a star is born. So once nuclear fusion begins, star is being made. Once heat and radiation is given off, that star is born. Number 5, most stars will spend most of their lives on the main sequence. Right, it's that long strip on page 15. And 6, once a star goes off the main sequence, it is in the process of dying out. Right, whether it's going to be recycled as a supernova, or it slowly dies into a white dwarf and into a black dwarf. Okay, so stellar evolution. The lifespan of a star is dependent on the original mass and size of the star. So once we get to this point where we have a massive star and a low mass star. All right, so it's mass and size as the key components. Larger stars have more mass, right? Smaller stars have less mass. So again, those are the 2 key components of where a star would end up, or the fate of that star. Massive star evolution. Once all the star's energy is used up, it will explode in the supernova event. This is for a massive star, a big one, right? The remnants of the supernova would result in 2 things. 1, a black hole from a very high mass, or a neutron star from just a high mass star. All right, low mass star evolution. Low mass stars like our sun, anything smaller, like on page 15, Barnard star. These low mass stars will not explode, so no supernovas are happening. Next one. Once nuclear fusion activities slow down, the star will eventually turn into a white dwarf. And eventually, once all the energy is used up, the star will not fuse elements together, and the white dwarf will turn into a black dwarf. So no radiation is giving off now; it's dead. All right. So our sun is an example of a low mass stellar evolution. All right, sample question. Which type of star is associated with the last stage in the evolutionary development of most stars? All right. All right. So most stars on that sequence, the very last stage. So you can actually refer back to page 15. All right. Most of our stars on page 15, medium size, low mass. Um, but the remnants, or what it will turn into, the late stage, would be a white dwarf, be a black hole, or a neutron star. All right, page 15. The earliest stage is the main sequence, right? The intermediate stages are supergiants and giants, but our late stage for most stars, again, right? Most of these stars, like anything medium size, like I would say Sirius, medium size and down. A lot of those stars are there, and eventually most of these stars will lead into the white dwarfs. All right, so we have newborn stars, and then from there, it will eventually die off. Right, we have intermediate stage, and we have our late stage. All right, so the best answer is the white dwarf. All right, summary. After this presentation, you should be able to know the 5 ways a star can be classified. 2, how to utilize the HR diagram on page 15. All right, we're going to have our activities on the next day pertaining to the reference table. A lot of that information. 3, how a star evolves from a nebula to the main sequence and to its final stage. 4, stellar evolution is dependent upon its initial mass and size. Massive stars evolve into catastrophic deaths, supernova. All right, and eventually into a black hole or neutron star. Low mass stars like our sun will evolve into peaceful deaths. All right, see you tomorrow. Be ready for the activity and maybe a small response question or two at the beginning of class. All right, so cooperation is needed tomorrow. All right, have a good night. Thank you.